this lecture we are going to introduce Verilog hardware description language, and particularly we also introduce hardware description. What is the hardware description language? So, here first we will introduce hardware description language, then what are the top down and bottom up design methodology, and then introducing Verilog HDL, and finally some example of Verilog HDL. So, here what is hardware description language? So, hardware description language actually we want to, let us say we want to describe the suppose we write symbolically some, let us say AND gate, okay, on AND gate A, B and output is Y. So, if we want to realize this algorithm, there are different level of realization or description. Suppose we want to describe the whole circuit in terms of transistor, that means you can use a CMOS transistor. So, you can initially use a NAND gate followed by a NOT gate, and then if you go to the NAND gate, what is the architecture? That means the NAND gate, we know that if we use this VDD, then it will go to our, so this is A, this is also A, this is B, this is B, and from here we tap our output. This point is, let us say, so we need two input like A and B, output of the NAND gate. So, it will be X and this is Y. So, this is our X, and then we will have simple inverter. This is X, this is again VDD, ground, and this will be Y. So, we can even describe this in the transistor level. Okay. Similarly, if you are talking about comparing, let us say we want to write Y equal to 1 if A is greater than equal to B, 0 otherwise. So, this circuit generally we like in terms of if else statement, how it can be translated into actual digital hardware, and we can go to a different level of abstraction, and finally it can come down to even the transistor level. Okay. And this is called hardware descriptive language, where you can describe the architecture of your implementation even up to the switch level, but generally people go up to the logic gate level, which are reasonably good enough. Now, so you can describe the digital circuit as a RTL register transfer level, that means you can go up to the logic block, that means you can use like AND gate, OR gate, like a latch circuit, a delatch circuit, like a D flip flop. So, by this way we can, using this common block, we can create a more complex block. Even if you want to go inside any, let us say latch circuit, or sorry, any flip flop or any gate, we can go to the transistor level also. So, we are talking about RTL register transfer level, where it will show symbolically in terms of AND gate, like a logic gates. Then we can do logic synthesis tool. There are very standard advanced tools are available. If you can provide RTL level thing to that tool, it will synthesize the VLSI IC, that means and gate level from RTL. So, it can make the ASIC from the RTL. And system level design also use, that means in the system level the Verilog hardware descriptive language can be used for prototyping using FPGA, and that we will be discussing in this course. So, that means HDL has benefit, you can visualize the circuit, your design into a circuit level or at least a logic gate level, you can optimize the timing diagram very precisely, and you can also prototype using FPGA. But if you go like for microcontroller, you have little flexibility because most of the architectures are already well defined. Okay. So, you do not have much access inside the digital block, rather you will have some either I would say high level language or maybe your assembly language, depending upon the manufacturer how they are providing for coding. But in HDL it is platform independent, whatever Verilog code you use you can implement in FPGA, and this can be also translated if you have a RTL file, any ASIC design tool like a Cadence, Synopsys, it can actually come out of IC out of this. So, it is a platform independent. So, popularity of Verilog. Verilog is very easy to learn. There is another harder descriptive language which is VHDL, but in this course we are primarily talking about Verilog HDL. There are different level of abstraction. I told you, you can implement in switch level. That means if you have an AND gate, you can break down into NAND gate and NOT gate, and you can further break down into CMOS transistor. You can also write in the logic gate. That means you can simply write in terms of AND gate, OR gate, or it can be RTL. That means it can be a combination of different logical block to make a one full design. Or you can also expand, and this is particularly for data flow modeling, where you can write in terms of various logic blocks are connected to make a complete circuit. Or you can represent behavioral level, particularly if you are talking about if-else statement, or you want to make a clock synchronized operation like a synchronous, or you want to implement a finite state machine. So, this can be in behavioral model. So, popularity of logic synthesis tools support Verilog HDL. Most of the logic synthesis tool like a Synopsys, Cadence, they support HDL, Verilog HDL. All fab vendor provide Verilog HDL like post logic synthesis, so that you can verify your design. You can, before you go for layout or your IC design, you can make a realistic case study, analyze the design. Then chip design using Verilog, there are many choices. So, typical design flow. So, usually in any digital design, you have to start with the design specification. That means what exactly you want to do. Do you want to, let us say, in our controller, we want to design a 4-bit ripple carry adder, 4-bit ripple carry, or suppose I want to do some adder circuit. First, I want to do an adder circuit, like I want a 4-bit adder. Now, this 4-bit adder will also give some specification. That means, what is the propagation delay that can be accepted, or vertical critical path delay that is acceptable. Then at what rate you want to compute, right? So, all this specification you have to provide. The 4-bit, is it a signed addition or unsigned addition? All this you have to provide as a design specification. Then it comes to the behavioral description. That means, when it comes to behavioral description, what is the behavior of the circuit? How does it change? And here it will go what type of architecture of the adder you will consider. Do you consider ripple carry adder, carry loop carry adder, or there are many other architecture. Once you decide behavior, then you need to go for registered transfer logic. That means you need to write, you have to go for RTL. That means you have to describe in Verilog HDL, you have to write Verilog HDL, which will realize this. So, in this course, maybe in our 66 lecture, in the subsequent lecture, I will show a complete implementation of Verilog HDL 4-bit ripple carry adder using Xilinx IC simulator. So, here then it will get a RTL once, and that will come using Verilog HDL. Once RTL you get, then you can do functional verification testing, and using Xilinx ISC I will show, that means different timing diagram, that means their functional verification, whether it is actually working or not. We have to make sure it is working. Then top down. So, suppose if you have a 4-bit ripple carry adder, 4-bit ripple carry adder, it can be realized by 4 full adder. That means, first is my RCA ripple carry adder top level, it can be broken into full adder, and one sub block if you design, that is enough. It will be just copied pasted. You will instantiate multiple times. One full adder can be realized by a half adder plus some other logic gate, particularly the OR gate, and this can be another leaf. That means, in the top level we want to implement a ripple carry adder that is broken into full adder, and there will be interconnection. Then full adder is broken into half adder and OR, and then half adder can be further broken into logic gate, okay, and that will be demonstrating in the subsequent lecture. That means, finally, in order to implement a ripple carry adder, you need to break down these pieces, and finally it will come with a logic gates. That means, it will end up with a logic gate, and by realizing the logic gate, you can actually go to implement a ripple carry adder. So, then it will go by the bottom up approach. So, top down will give you the insight how to break, and finally, when you implement, you have to go by the bottom up approach. That means, you take one half adder. So, half adder consisting of what? So, here let us take half adder will be some logic gates. So, let us say I am talking about some logic gates. There can be multiple logic gate, then it will constitute a half adder, then half adder to let us say it will go to full adder, then you go another level up, then you will get a ripple carry adder. So, by that way you can implement. So, bottom up means, that means in the Verilog module you have to create a basic module, that means you have to create a half adder basic module, we have to create a full adder basic module, and then it will go up to RCA module. So, that means it will go by this chain. So, this is called bottom up approach. What is a module? In a Verilog we will write in module. So, module will describe a particular you want to realize, let us say we want to build a half adder circuit. So, then it require a module. So, module to describe a block in Verilog HDL, and module consists of a basic block, or it can instantiate multiple modules, sub module also. Then higher level blocks get necessary function through port. That means, if you have a ripple carry adder, then RCA, what will get? You will get a vector data of A, vector data of B, and you will also get one carry in. And what will be out? You will get sum and you will get carry out. But inside, when you are realizing ripple carry adder, you will have multiple full adder circuit. That means, you will have full adder 1, full adder 2, and how they are getting interconnected, that will see in subsequent lecture. So, the intermediate interconnection will not come as an input output port. So, input output port only will consist of the data, vector data, which are A and B, then carry in and sum out vector and carry out. Then designer can modify module internals by not affecting other block. That means, you may not, that means output block will remain same, ripple carry adder will remain same, but inside there are different level of abstraction which can realize a ripple carry adder, either by breaking into pieces and make the ripple carry adder starting from the logic gates, or by means of data flow modeling you can come up with one full adder or maybe a total ripple carry adder just in one comment, that is also possible. So, how to define a module in Verilog? So, Verilog, the module and the end module are the keyword that will start, then you have to write a module name. Let us say I want to write a, let us say an AND gate or maybe a half adder circuit, right. So, how does the half adder circuit look like? That means, you will have an XOR of a two signal A and B, which will be sum, and you will have AND of this signal, this will be carry. So, this is my half adder circuit. So, you have to write a module like this is the keyword and there will be n module, then you should write a half adder, that is name of the module, and you have to declare the port. So, here I will write A, B, sum, C, then you have to define what is my input. Here input is A, B are the input, then you have to define output which will be S, C, then you have to write how they are realized, that means actual function block to realize. So, here since the math we will be demonstrating that there are some built-in primitive in HDL, that means you can write XOR, it is a built-in primitive, you have to give an instant name, and built-in primitive the output will come fast, that means sum is the output, then A and B is the input, and then we will have an AND gate, again it is a built-in primitive, gate 2 it will come as a common A, B, again output will come, and then you will do N module. So, N module will use a different color, that means we will do N module. So, that means Verilog have this input output port declaration, and we will discuss more detail about this. Okay. So, that means we can have this keyword. So, these are the, it will look like this, and you can get detail about this in Samit Palnitkar book, different level of abstraction. So, there are 4 level of abstraction. One is the behavioral model, which is a very top level, and we will discuss in detail about in other subsequent lecture. Data flow modeling, gate level and switch level model. And we can, in order to design a circuit, in fact when you go for a more complex design, it may be difficult to go always in the gate level. So, you have to mix it, but we should make sure that whatever level you write, the synthesizer should understand that what circuit you are trying to imply. So, that is important, and we will use mixing all this level of abstraction to implement a very complex algorithm. So, module, inside a module you can, like inside a full adder module, you can instantiate multiple sub module, which is like a half adder module, and half adder is a separate module that we have discussed. So, you can instantiate how many times you want. So, as if one half adder module you built in, but you call multiple times, so it will connect multiple half adder. So, these are the instances and we can instantiate, but no module is defined. That means we cannot write another module of half adder inside the full adder module, that is not permissible. Module are invoked by instantiation, name of the object is called instances. So, these are the instances we have to be separate out, and a module must be defined before instantiation. That means, whenever you execute this full adder circuit, you must have a functional half adder module ready. Example, if you instantiate a full adder module, this is way, but we cannot use another half adder, another module for half adder. This must be avoided. This is not permitted, but we have to separately create a module for half adder, and you can call it inside this full adder module. This is not correct. Component of Verilog module name, list of port I define, declaration of port whether this is input or output, then declaration of parameter if it is required. That means sometime for controller you need to specify Kp, Ki value, Ki, Kd. Then declaration of wire, because there are some intermediate interconnection which are not connected to the input or output port. So, we have to declare out of this which are wire or which are register, and then we have to instantiate lower level module, particularly when you call instantiate, let us say in a PID controller we can separately have a modulator, we have Kp block and other block, or in a full adder we are instantiating a half adder. So, this instantiation lower module, but we have to, it can be variable or data flow. We can also instantiate some task. Example of a module, it is a half adder module I have discussed. So, that is, this look like a circuit, and this is the XOR gate and AND gate. So, this we have already discussed. A module cannot contain, so it may not contain all component, right. A module defined but does not have a wire or register, because they are all connected, but sometimes there can be multiple circuits are connected, but not all the interconnection points are available in input output. In that case, you have to define wire or register whatever inside variable. Then declaration of port allow a module to interact with the environment. That means the port like an IC, if you have a like say IC pin. So, ports are like IC pins which interact with the external interconnection. So, we have to define input or output port. What are the port? Sometimes the input can be a vector or a scalar. So, it is a vector, you can combine what is the vector size, whether it is a, in case of 4-bit data you have to write input, then 3:0 like A comma B. These are the 4-bit data where A3 is the MSB and A0 is the LSB. Okay, so you can define this module. There may be module which do not require port, because some intermediate module may not require ports. Okay, connecting port to external signal. So, that means if you have this full adder circuit consisting of half adder, so half adder are inside. So, the half adder may not be connected with the real world, full adder is connected. This looks like the structure where these A, B, C are the external data which are interacting with the external world. The full adder, this is a half adder circuit. Then inside half adder there are some intermediate signal where you may not have external connection, only some carry out A, B, C, these are the input which are connected externally. Then connected port to the external by name. So, here by sequence order list. That means when you call a half adder module, you see S1, C1, A, B, there is a sequence, first sum, then carry, then A and B data, and this must be consistent with the one here. That means SCAB. That means, if you write, let us say first you are writing sum, then A, then B, then carry, then you have to change also. In this case it will be S1, then A, B, then C1. So, you have to change. So, this is like instantiating module by their sequence order list, but this may be difficult if we have multiple input. How their sequence are connected, it is difficult, but we can always remember S stand for sum, C stand for carry, like this. So, there are, you can have many such signal. The second option is that module instantiation by their name, where the dot S, dot C, dot A, it is case sensitive, it must match with the dot of this. That means, you copy paste the half adder. So, first you can do, you can copy a half adder circuit, you can put let us say instantaneous name, then you first here S as per this and put a dot, then you put C, put a dot, then dot A, dot B, then you put a bracket where you give the local variable. So, some of this half adder is connected to the S1 output of the full adder, that means S1. Carry out is connected to C1, that is the internal connection. A connected to A, B connected to B. So, like that way we can connect. So, this inside are the local variable and these are the actual, it is the original. So, this is by name. So, by that way, even if we interchange the sequence here compared to here, it is not a problem. Only thing, the name must be consistent with this name, and you should connect the right local variable to this where it is connected. You have to make sure these are consistent. That means, in this case you can also write, instead of or alternatively you can write like alter, you can write alternatively you can write half adder G1. Here you can start with C, no issue, only it has to be C1. C and C1 are connected. You can put A, no problem. Then you can give S, then you can give B. So, this is permitted as long as you define by name, but earlier case it was not the case. Okay. So, stimulus block, similarly I will show in the, when I will show the Verilog Xilinx IC simulator. The stimulus block depends on what simulator you are simulating, because Verilog code is common, you can use any platform for simulation or synthesis, but when you actually simulate, then you have to use what simulator you are using. So, here we will be using Xilinx ISC simulator. So, I will show you how to simulate using Xilinx IC simulator. Okay. So, right now we are just saying that in order to test any design block, you need to generate some pattern of input and output, so that we want to check whether the output is working fine or not. So, you need a stimulus block. So, in summary, we have introduced Verilog, like we have discussed hardware description language, then we talk about top down and bottom up design methodology. We have introduced Verilog hardware descriptive language, and we have considered some examples of Verilog HDL case study. That is it for today. Thank you very much.